Hi and welcome to my presentations, Hierarchical Human Motion Predictions and Logic Geometric Programming for Minimal Interference with Human Robot Tasks. So blending robot motion in a dynamic environment working with humans is very challenging. The robot must not interfere with humans or even collide with humans. So the ability to forecast the human motions and the robot blending capability to adapt to current environmental conditions are very beneficial. So in a paper, we propose a hierarchical method to predict long-term human motions and also propose a task and motion blending method to adapt blending to current environmental area. So it has been shown that a recurrent neural network predict very good result with short horizon. However, with longer horizon like 3 seconds, the prediction of human in red and the round truth in white starting to diverge. And this work also have no notion of task context, so it is unable to predict based on the task conditions. Our robot blending is built upon the logic geometric programming approach. So it is a task and motion blending approach. In that particular, is a nonlinear program optimized for robot trajectory, where the inequality and the equality constraints are defined by the symbolic state action sequence land at the symbolic domain. So this method had the ability to reduce long-term optimized local paths with satisfying the constraint to define for the robot scrapping or collision avoidance. In our approach, there are two components. The first component is human motion predictions. So at the high level, we define a symbolic domain for the human. So given the start state and the goal state, the high-level policy will produce a sequence of action. So from the human sequence of action, we will derive a human sub-goal to fit into the recurrent neural network to reduce for human trajectory. So our second component will be in form of the human trajectory. At the trigger blending at time t, the symbolic deduction model will be in form of the human state and then produce the current symbolic state st, and together with the current geometric state of the environment and the goal, the nonlinear program here will optimize for the task trajectory. So the robot had to follow the task trajectory in order to complete the task while minimal the interference with the human. So this slide will talk in more detail. So our human motion prediction is an encoder and decoder architecture. So given the initial human trajectory from time 0 to time t, we input the human position and as well as its velocity to the encoder. And in the decoder, we will output the future human motion predictions from time t to final horizon. But as you can see, the looping back architecture of the decoder will accumulate the error, small error over the long horizon. So in order to mitigate that effect, we input the sub-goal for each RNN itself given by the high-level policy mentioned before. So this has the effect to condition the prediction based on the task context. Now we turn our attention to dynamic algebra. So given the current symbolic and geometric state, the robot path will be optimized by minimizing the following cost function. So this cost function penalizing the velocity and the acceleration of the robot, and also condition on the sequence of symbolic state. So this cost has some constraint. The goal constraint will guide the robot to the final goal, and we also have the phase constraint, in which we can encode the collision avoidance behavior in the phase constraint, and also the switch constraint. We can encode the the robot scrapping behavior or other switching constraint at the switch constraint. And also this regulate the state transition at the symbolic domain, and the final symbolic state must be in the set of the symbolic goal. So in order to solve this NLP, we first search for possible candidate skeleton from 1 to k that lead the symbolic state to the goal. And then for each of the candidate, we optimize an NLP instant for that candidate using the interior point method until a feasible skeleton default. So this is the example of symbolic deductions. So given the snapshot of the environment at time t, as you can see, the robot is holding the bread plate and the human is holding the drink cup. And also there's various objects at the table and the shelf. The symbolic state will be deduced into this. So this is the mechanism to reduce the symbolic state. For example, if the robot is carrying something, we check in the kinematic tree if we exist a stable jump from the robot to the object. So how do we inform the dynamic eligibility of the human state? There are two aspects. So given the trigger planning time at t, we have the environment. Then we will derive the symbolic state st from the geometric state of the environment, and then we will input port the symbolic state and the geometric state to the NLP. And at the same time, we compute the side distance map from the environment. The circle here will be the obstacle module, and then we can compute the side distance functions and forward to the phase constraint given by the soft mean functions. This constraint will have the effect to for the robot to avoid the obstacle, and the human will be treated also as the obstacle in the side distance map also, and it will be updated each time the blending is triggered. Now for the experiment, we use the Moge datasets to train for the human prediction model, and we also use the dataset object to as a case study for combining the human motion predictions and our robot blending method. So this is the result, compare the human motion prediction with go input and without go input. And you can see without go input, the human failed to reach the object, while our hierarchical method can. In the video, you can see better the long-term human predictions. The red point is the sub-goal. As can be seen, without the sub-goal, the average joint error and the position error is much higher than with the goal input. So this will compare the single blending and dynamic blending given the human trajectory. In the single blend, it's treated at the worst case scenario where every pose of the human in the trajectory will be treated as obstacle, and the robot will optimize for its long-term trajectory only one time. And in the dynamic run, the robot will be triggered periodically given the current symbolic and geometric state of the environment. And as you can see, the dynamic blending can produce a much more reactive path, and it's much shorter than the single blending. So we evaluate our experiment with 63 task instances, and as you can see, the dynamic blending has a much more success rate to complete the task and reduce the path almost half of the single blending. So in this work, we propose an approach for long-term human motion predictions, and this can also adapt the human prediction to the task context. We also extend the LGP method, the ability to replan the robot planning to adapt to environmental error, and we combine both approach to solve for the human-robot collaboration task. So in the future, we will include the collision avoidance in the human motion predictions and full treatment of the robot's wrapping constraint in long-term robot planning. Thank you for listening.